Hello, I'm Indiana Jones. I'm in the middle of this fabulous temple. But this temple is collapsing, the enemy is destroying it. And I have this knapsack, and this knapsack is full of very valuable things. And I'm going to show them to you, right? So we have this fantastic book. Indiana Jones is reading about computational complexity. Indiana Jones loves physics, quantum theory. No, this is ginger beer, Australia, best secret. This is the first computer, okay? So the only stock of this beautiful computer is actually at MIT at this point. Let me see, what else? Ooh, I have this beautiful Chinese artifact coming directly from Tsinghua University. And then, the best of all here, I have this very, very valuable Japanese artifact. Very heavy. And so Indiana Jones has to decide which of these items he's going to be putting inside his knapsack such that he can escape the temple before it collapses. Okay? And of course, you know, Indiana Jones is lucky. You know, he has this beautiful, beautiful textbook about computer science. So he's looking, you know, knapsack problem. Okay? And then this textbook is saying, oh, the knapsack problem is NP hard. What does that mean? That means that this problem is intractable. Ooh. Oh, but there is hope. There is hope. Approximation algorithm. Ooh, but the knapsack problem, the multi-knapsack problem cannot be approximated. Okay, so let's look. P-space hard. Oh, that's even worse. Intractability. So Indiana Jones is completely lost. He doesn't know what to do. But he remember that when he was young, he took this Coursera class on optimization, and he knew exactly how to pack this knapsack. So he packs the right item and escape, and everything is fine afterwards. Well, this is what this class is about, okay? So what we are going to talk about in this class are optimization problems, like filling a multi-knapsack or like filling a knapsack. And these problems are called optimization problems, okay? So these are, as I just said, very, very hard problems. They are among the hardest problems in computer science. And we'll talk about it. And this is a very, very well-defined class. They are called NP-complete. Okay? And what is an NP-complete problem? So, you know, I'm going to define that in the next slide. But essentially, these problems are everywhere. They are running the supply chains everywhere in the world. They are scheduling the sport leagues. That's really important, right? They are scheduling logistics systems. And, you know, a country like Australia spends 10 to 20% of its GDP just on logistics. You know, they are basically running the electrical power system, okay? And many of the manufacturing firms all around the world, okay? So I told you that they were they belong to a complexity class which is called NP-hard. And that complexity class is basically dealing with decision problems. So the question that this class is looking at are problems like, can I fill this knapsack that I have here, okay, for a value which is above k, okay? And so informally, these NP-complete problems will have two properties, okay? The first one is very interesting. If I give you a solution, you will be able to verify that this is actually indeed a solution very quickly. So you have very efficient algorithm for checking if something is really a solution. If I tell you how to pack this knapsack, you will be able to verify that you can actually do it. And it's the case for all the problems that I've shown you before. If I give you a sports schedule, you will be able to verify quickly if this is a real schedule, or if two teams are actually playing twice on the same day, okay? So you can do that. And the second property, okay, is that if you can solve one of these problems, okay, one of these NPR problems, then you can solve all of them, right? So you can focus on one. If you can solve it efficiently, okay, you will be able to solve all of them. So this is essentially what NP-completeness is about. These two properties, you can check very quickly, and if you can solve one of these hard problems, you can solve all of them. But as I told you, they are supposed to be very hard. So in theory, everybody believes that solving these problems is going to require exponential case. An exponential case is an exponential time in the worst case. An exponential time is kind of a nightmare. It basically means that if you increase the size of the problem by 1, you double the time. And so you can only solve very, very, very tiny problems. So, you know, what I told you is that they are very, very hard problems. But I also told you that they were everywhere. Okay, so this is logistic, right? So, if you look at the country like Australia, which is importing a lot of goods, they come to the harbor, let's say in container. This container is to be offloaded from this ship. The cranes are going to take them. Straddle carriers or RTGs are going to move them inside the port such that you can put them on the rail, or on tracks. Okay, this is full of optimization problems. Once you have these containers that are in a yard, you have to schedule all these trucks such that they deliver these containers to the customers as quickly as possible. Another optimization problems. And these problems are obviously solved every day. Okay? Energy. Energy is an area which is full of optimization problem, because what? Energy is about meeting the load, making sure that the load, the demand and the generation agree. So every day, many companies around the world are making sure that these two things are matched, at every minute, at every hour, and so on. Okay, and that requires something actually very complex, optimization problem. Just use Google. Google unit commitment. You'll see a huge number of papers. They are just trying to solve some of these problems. Okay, and then obviously sports scheduling. We all love sports. We can't live without it. So this is essentially an NFL schedule for one of the seasons. Okay, so you see Tennessee over here, which is playing first at Jacksonville, then at Jacksonville, then at home again, Baltimore, Denver, and so on. Actually, producing these schedules is very hard. Why? Because you have a lot of constraints. Okay, so you don't want a team. Sometimes some of these teams are actually sharing the same stadium. So unless they play against each other, they can't use the same stadium. Other stadiums are actually shared by baseball and football teams. So you can't schedule a baseball game and an NFL game at the same time. Then you have all kinds of constraints on the kind of schedules that you want. You don't want a team to play 3 times at home or 3 times away. Fans would actually lose interest. If the team never comes back home, if it's always away, fans are actually losing interest. And also the schedule is too hard for these teams. So you need to balance the pattern of these games. And then finally, you want to have this schedule such that the television network are happy. Okay, so you want that the nice games are scheduled, on Sunday night, on Monday night, and you have to balance that across the season such that you don't always show the same teams. Okay, so scheduling all these things and optimizing this function is really, really hard as well. Okay, so what I've shown you is essentially a set of problems that we have. We know that they are very, very difficult to solve. They are very important, but they have this exponential behavior that you see here, right? So this is the size of the problem that you see on the x-axis, and this is exponential runtime. At some point, it becomes really, really bad. Okay, so in the particular case that you see here, essentially, in between 100 and 150, let's say it's a logistic problem. These are trucks, okay? Between 100 and 150 trucks, the runtime is taking so long that there is no hope of solving the problem. So what are we going to do? We know that in the worst case, we will have this exponential behavior. So one of the rules of this game, one of the games here that we are playing in optimization, is to try to push this exponential. We try to make sure that we can actually solve the real practical problems. And in this particular case, there may be around 200, 300 tracks, or maybe 2,000. We try to push this exponential so that we can actually solve practical problems. Okay? Now, this is very difficult to do, and that's why we are teaching this class, obviously. Okay, but sometimes it's so hard that we can't actually do it. So what we have to do in those cases is to say, well, this is really too tough. But we still have to find a solution in practice. So what we can do is actually lower our standards. We are going to say, finding the best possible solution is this humongous set of possibilities. It's just not possible. And what we're going to do is simply say, okay, we'll find a very, very high quality solution. It's not going to be the best, but it's going to be really close to that. Okay, so that's the other kind of techniques that we will see in this class. Okay, so 2 things. We'll push this exponential, or we will, or we will actually try to lower the standard and find high quality solution easily. So let me try to summarize what we have said so far. Okay, so optimization problems are everywhere. Okay, now we know from theory that they are incredibly hard to solve. But we know also that we need to solve them, and we'll see techniques to actually trying to push this exponential or lowering our standards as little as possible. Okay? So one of the things which is really interesting here is that these problems are really fun, okay? So you'll see, it's like playing a game. It's man against the machine, and we want to win, okay? So this is a very fun classes of problems because you have to think about ways of actually defeating this complexity. And then one of the things that I want to focus on in the last couple of slides here is to tell you that for some problems, they are really, really important to solve. You really want to solve them because they make a big difference in the lives of people. And I'm going to give you 2 examples, okay? So the first one is about kidney exchanges. And so the basic fact here medically is that everyone can live with 1 kidney, okay? But every year there are about 80,000 patients, let's say in the US, who are requiring a kidney, transplant. About 4,000 of them every year are going to die because the kidney transplant is not ready. And the reason why that happens is that there are compatibility issues, and I'm going to explain them to you. So essentially, what you see over there, okay, is a mother and a son, and the son needs a kidney, okay? And the mother, obviously, being a mother, is going to be willing to actually give one of her kidneys to the son. But the problem here is that she may not be compatible with her son. She may not be able to give her kidney such that the son is going to accept it. Okay, the son would reject it. Okay. On the other hand, my wife may need a kidney, and I may be willing to give one of my kidneys to my wife. But once again, I may not be compatible with my wife, at least, from a kidney standpoint. Okay? So what can we do? Well, maybe I am compatible with the son of that, lady, and that lady is actually compatible with my wife. So instead of doing, this transplant in a vertical fashion, we can just do an exchange. I'm giving my kidney to the son, and this mother gives a kidney to my daughter, and everybody is happy. Okay? So that's the key idea here. Okay? And obviously, in practice, I told you, we have 80,000 people who are in need of a transplant. So what we are going to look at is a big graph of all these people, these pairs of donor receivers. And so what you see on the screen here is essentially all the pairs, it's a small graph, but you see all the pairs of donor and receiver. So you see here a donor and receiver. This person is willing to donate a kidney. This person here needs a kidney. And when I have an arrow here, it basically means that this donor is compatible with that receiver. So this donor can actually give, her kidney to this person, okay? And so you're going to see another set of arrows here. So this particular donor here can give also a kidney to this receiver. No, this is a good situation because at this point we can do an exchange. And of course we may have a really huge graph like this. Here you see that this particular donor can give to this receiver, but this donor is compatible with only that receiver, and that particular donor is compatible with that receiver. We have another cycle. It's a longer cycle. It's three edges in this particular case. Okay? And of course now we have cycles all over the place here. And the goal here is to try to cover all these pairs with these cycles. Okay? Now we can take this graph and simplify it, okay? Because it really doesn't matter that we have pairs here. We will have an arrow when there is compatibility between the donor and the receiver, and when another arrow is the donor for this one compatible with the receiver over there. And now we are looking at this graph, right? So you see this graph. And what we want to do is essentially cover it with cycles, okay, such that we cover as many of the pairs, the nodes that you see in this graph, okay? Of course, a node cannot happen in 2, cycles, because otherwise it would mean that you would be donated your kidney twice, okay? So what we are trying to do is to cover this graph with cycles such that every node belongs to exactly one cycle, okay? So this is one of them. Okay, so you see this beautiful blue cycle here moving from these donor pairs to other donor pairs and so on. And if you apply this, we are basically saving 4 people, and there are 4 more people that are left without kidney at this point. They may receive a kidney later, but at this point they don't have one. Okay, so this is another way of covering this graph here. Okay, so you see one of the cycle here. Okay, chuk 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 chuk, and you see another one here. Chuk 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 chuk. Okay, I'm showing it to you now. Okay, and so in this particular case, if we apply this covering Okay, so we save 6 people and only 2 are left waiting for a transplant at this point. Okay, so now you have to imagine, okay, so this is tiny, right? This is easy, we can do that by hand. Okay, but in practice, I told you we've had this gigantic graph with about 80,000 nodes. Okay, and now finding the best covering with cycles of these nodes is really becoming a very interesting problem. So if you take this class, you will learn the techniques to actually do that. Okay. So let me talk about something completely different, but which is also very close to my heart, which is a problem that we've been working on, for about 5 years now, and this is called disaster management. So this is an example where you see this is a hurricane of category 3. It's actually Irene that hit the United States in August 2011. There were about 56 people who died in that particular. Due to that particular hurricane, and essentially the cost of that hurricane is estimated to be about $15 billion at this point. So you see the picture of this hurricane over here. This is another picture. This is really a scary hurricane. So one of the things that we have in this area is that we have very good prediction algorithm to actually predict what the hurricane is going to do. You see that here. You see the prediction, and you see the cone over there. You see one path and the cone. The cone is typically about 80% of the path. Okay? And so in a sense, you have a lot of information about what this path can do. Okay? And so one of the things that this hurricane are going to do is basically create blackout. And so what you see here on this picture, okay, are basically all the blackouts on the east coast of the United States, which were created by Hurricane Irene. So I was living at the time in this particular circle over there. I was teaching fabulous undergraduate at Brown University. Okay, Nabil, this is for you. And essentially these places had basically a blackout of about 5 days. Now, can you imagine what it means to be in a blackout for 5 days? So this is what is happening to you. Okay, so no electricity, no refrigeration, no air conditioning, no mobile phones after a while, no Facebook, nothing, right? It's really boring. And after 5 days, you are ready to, do something radical, okay? So this is another example which actually created exactly the same thing. This is Hurricane Sandy, actually much more damaging even, okay? So once again, what we had were very good prediction. You see the path of the hurricane, and they predicted that it's going to turn, and it actually turned exactly, almost exactly when they said it would turn, okay? And it created massive floods that you see there and massive blackouts, okay? So this is a picture of New York City during Sandy, okay? So it's beautiful pictures, of course, blackout everywhere, okay? And so essentially what we try to do in this particular area is trying to restore electricity as quickly as possible. We try to reduce the size of such a blackout. So you want to repair the grid as quickly as possible, and the way you have to do that is essentially sending crews to repair various parts of the grid, okay, such that you minimize the size of the blackout. You restore a line, you restore a generator, and things like this. And what you want to minimize is the size of the blackout, this red area that you see over there, okay? So what you see in this graph, the x-axis is essentially time. The y-axis is the power that is flowing inside your network. Obviously, you want to be restoring the maximum power. And every point that you see there is a restoration action. It means that a repair crew came and fixed the power line, and now the current is flowing again. Okay? And so sometimes you restore enough that the power flows a bit more. You restore more power flows in your network. And so what you want to do is schedule all these repairs such that you minimize the size of this blackout. Okay? So this is basically combining two problems, okay? So the first problems here is, basically a logistic problem. You have to have these trucks pick up some parts, okay, such that you can actually go to the particular sites where a line needs or a generator needs to be fixed, and you actually fix it. That's the pluses that you see there. The minus that you see over there are basically places where you pick up some parts, okay? Now, every one of these restoration actions corresponds to something that you see on this power graph here. Okay, so it basically means that when I repair that particular component, no more power is flowing inside my network. Now you have to synchronize these two things. Okay, this is a pure logistic problem. This is a power restoration problem. Now the difficulty that you have is essentially that this thing here, okay, the power system is regulated by these power flow equations. Okay, So, and Carlton and I, you know, Carlton is the head TA of this class, have basically spending 4 or 5 years looking at this thing to try to solve them better. It's really, really complicated. But you have to, you know, you have to combine that with the logistic problem, okay? And so this is amazingly complex, okay? But once again, if you take this class, you will learn the techniques to actually do that. And what are the kinds of results that you will have? Look at this graph again. I told you time. You know, I told you power flow. This is essentially what this is the state of the art in practice. That's the restoration if you use the techniques, let's say like 4 or 5 years ago. And this is what you can do with the algorithm that we have designed. You reduce substantially the size of the blackout, okay? Once again, if you take this class, this is the kind of reduction this is the kind of results that you will be able to produce. Okay, so welcome to Discrete Optimization. This is an amazingly interesting class. It's an introductory to Discrete Optimization, right? So you will start from almost nothing and build up all the tools to actually solve some of these problems. But it's an introduction. It's also a very, very difficult class, okay? So you will have to work very, very hard. So think twice before taking the class. Thank you.